let's talk about predicting whether we have an increase or a decrease in entropy in different situations, because I think this is a little bit difficult for some folks. All right, so I'm working off an end of chapter problem in your textbook, end of chapter problem 19.43. So if you want to go back and look at that, hopefully there's no errors in this one. All right, so let's look at this equation. We've got nitrogen gas plus hydrogen gas, and we're going to form ammonia. Great. Okay. Awesome. So in this process, we're going to have some change in entropy. All right, we always do in any process, unless it's a reversible process, and then we might have an entropy change of 0. All right, so what are we doing? Is our system going to be gaining in disorder, or is it going to be losing or gaining in disorder? That's kind of a funny way to put it. Is our system becoming more orderly or less orderly? Ooh. Go ahead and talk to each other. What do you think is happening to the order and the disorder? Think about microstates. Might be important, but I'm not convinced. Like it could.
I feel like it's mostly the size and the fact that it's a full outer ring.
Yeah, but still, like this is going to be like a pretty cloud too. I mean, this should have more mass, so it should have stronger forces. It should have higher. So I'm going to have to go back and look at it.
I'm just looking at this like if they're not going to want to be together, and the only reason they become solid is going to get slammed if they're moving apart. And then I don't know if there's any becomes a real solid. It might just be a semi-solid.
I think it depends on if you get it cold enough, it'll crystallize for sure. All right, thank you though. I appreciate that. All right, guys, what do you think? Are you going to have more microstates possible on the left or more microstates possible on the right? Who says more left or more right? More left, right? We have more microstates on the left. So are we gaining in entropy or are we losing entropy in this process? What's our sign? Negative. We're losing entropy, all right? We've got a change in the number of moles of gas. We're decreasing in moles of gas. All right, let's look at another example. All right, we've got, what's the name of this? Calcium carbonate. Good. All right. Calcium carbonate. So it's going to decompose. What's the name of this? Calcium oxide. Y'all better know what that is. All right. So we've got this decomposition reaction happening. So you guys tell me, are we gaining in microstates or are we losing microstates? Gaining microstates. This is a pretty obvious problem, right? We're producing gas, which is wild and crazy, and it's going to be moving all over the place. So our delta S is going to be positive, right? We have a gain in entropy. We've gained in disorder by this process. We have more microstates available in the system. All right? How about this reaction? 3C2H2 gas. 2C6H6 gas. Okay. How about this reaction? What do you guys think? Have we gained entropy? Have we gained microstates? Have we gained disorder? Or have we lost entropy? We've lost entropy. We had 3 things, right? 3 things to make all different kinds of permutations. Now we have 1 thing. Wah wah, right? Our delta S is negative. Okay? All right. Now here's kind of a tricky one. So we've got aluminum oxide and hydrogen gas that's forming solid aluminum and water vapor. What do you guys think? Go ahead and talk to each other. What do you think is happening with the entropy? This is very tricky. All right, so coming back together. This is kind of an unfair one because the answer is that delta S is very, very small. The change is really not too significant, and it's probably positive. All right. Now the reason why, and the book again sort of like does a cop out on this one. I think it's kind of a weird one to be asking you guys, but I think that it's slightly positive, and we haven't changed in the number of moles of gas, right? So you might think, well, it's 0. The only reason why I'd say it's probably close-ish to 0, but on the positive end, the only reason why I think we've gained in entropy is look at the structure of hydrogen gas and then the structure of gaseous water, right? Which one's more complex, this one or this one? The water is more complex, right? So if we start thinking about the different kinds of motion, right? You can have more kinds of rotational motion, right? We've got two bonds now to rotate around, right? There might be some more interior motion possible, interior microstates that would tend this to be more like delta S being positive. So is this really, is this one I would put on an exam? What do you think of me? Yes, probably. No, but actually no. I probably wouldn't put this on the exam because I don't know that I would expect you necessarily to be looking at this structure and thinking, well, yeah, but rotation possible, okay? All right, last thing, real quick. Do look back at the Gibbs free energy stuff. Do look back at those slides where I talked about biological relevance. Anything that we discussed in lecture 2 that came from chapter 5. So anything about a closed system versus an open system. Anything about sign conventions for exothermic and endothermic reactions. Anything like with it gives free energy. If I want to have an exergonic reaction, what signs of enthalpy and entropy will always give me an exergonic reaction? Do I need to say that one more time? Okay. So if I asked you what signs of enthalpy and entropy would always give me an exergonic reaction, that might be a good question. All right, what signs of enthalpy and entropy would always give me an endergonic reaction? You should be able to tell me that. Okay. That's all I have here. I hope that you guys have a great time studying, or at least not too painful time studying, and I will see you all on Monday or Tuesday.